All right, hello everyone. I'm Jørgen, and today we're solving this problem. Pip install my project. This is all about really providing something for your users in Python, which is a pretty good language for a lot of users, especially new to programming, for doing high-level descriptions of their problems. But it often comes with some issues. And for us, the challenges are really, like, I want to use C++. I want to use C++ to provide speed, to integrate with other solutions I have in C++, and also to provide a sort of statical framework for me to work with, because sometimes refactoring in Python can be a little bit difficult. And also I want to install this on Linux, Mac, Windows. There's also the BSDs, but they're sort of an exercise for the reader. As a proxy for me, I'm going to use Mekazava. I'm not very fond of using my own name, so I'm going to use Mekazava. He will show up in where you would substitute yourself. So that's a pal of mine. So let's start with pip install. Pip install is one of those things that if you're developing Python, you're using all the time, and maybe you never really thought about how it actually works. It works in 4 main steps. The first thing it does, it looks up the package you're looking for in an index. Usually that would be PyPI, but it can in principle be any compatible index. It's just a package registry. Then it determines if this particular package is installable. If it's there, and can I install it? To do that, it looks at the host system, it looks at your Python version, and whatever is available in said index. After that, it'll fetch the package, and finally extracts the contents of this package into your side packages directory. That's really it. Most package managers, honestly, work that way. That package can be constructed in several different ways. I've chosen to group them into 4 main categories. You have your pure Python. This is what you would usually want to write, and especially your downstream users, you would want them to write this. So that's when you have all Python code in your .py files, and it's just Python, you know. And you have the thing I've chosen to name impure Python, which is almost indistinguishable from pure Python. So this is Python code that uses a non-Python backend. Probably the best example of this is NumPy. NumPy has a backend in C, and you never really notice. It looks and feels and behaves like Python all the way, but it's just a lot faster, because Python is quite slow. You have what I choose to call thin library wrappers. So imagine you have your system library. It could be BLAS, it could be LAPACK, it could be anything. That you then make a thin wrapper in Python around. They would typically operate in a sort of fire a request to the library, wait for it to finish its routine, and then parse its results, pretty much like a subprocess. You would treat the library like a subprocess. Very often you would use C-types for this, which is the Python foreign function interface for libraries. But that's not necessary, but it's that style of libraries. They look very much to like the host library that they're integrating against. And there's the fat wrappers. So they differ from the thin wrappers really only in the sophistication of their interaction with the other library. Is there a lot of communication back and forth? Does it maybe provide progress sometimes? There's input-output, you modify state, and you do all of this, but from a Python setting. The big difference between this and the impure Python library is that the fat library wrappers typically target something that is also available from other programming languages, whereas in the impure Python case, in NumPy's case, the backend is really only available in Python. This talk will largely cover the impure Python and fat library wrapper setting, but it is also applicable to the thin libraries. This is a packaged Python. It's from the terrarium at Akvariet in Bergen, which is now my hometown. And I just wanted to share that. So the question then is, what is actually inside a package? What's in a package? This is a pretty common layout. I stole this from the docspythonguide.org listing, but your run-of-the-mill Python project would be laid out like this. You have some metadata in terms of, like a README. You have a license file, some requirements that you would need to be installed with the package. You have docs, and hopefully you have a lot of tests. And of course, it's my package, in this case, source directory. This is where all the source code goes. Python is pretty opinionated on how this source code directory should be laid out, because Python libraries are really just directories with a specific structure that Python then knows how to interpret. OK, so we let out a project like this, and then we run the setup script. We'll go into the actual details of the setup script later. But when you run that, you will get, with the command bdiswheel, which means binary distributable wheel or something, you would get what is really a zip file in disguise. If you just list the contents of that, you will see a lot of files that weren't in the original source directory, like the metadata, the wheel, and the record. But there's also the license file, and of course our source files. Pip knows how to take this structure and unpack it into your side package directory, which is where Python stores its libraries. And you will see here the my package from their source directory being laid out next to NumPy, to Pandas, to Minisat, and all your other installed Python libraries. And that's really what a package is, right? It's just this intermediary format that you can give to someone that their tools would know how to unpack into something that they can now just run. This is the Pantheon in Rome. Arguably one of, if not the most gorgeous building in the world. If you haven't seen it, then order a plane ticket right away. I'm bringing that up because the Pantheon is a living piece of history in Rome. And it's quite important to understand and appreciate history in order to provide some context onto why things are the way they are today. History is that context. So let's look at that for Python packaging. In the late 90s, the Python community realized that they wanted something like the CPAN for Perl, the Comprehensive Perl Archive Network. CPAN is arguably one of the reasons Perl had such a massive success in the 90s, and it was pretty glorious. It was very easy to get and obtain and use software, and there was a massive wealth of packages available. And Python didn't want to be any worse. They wanted to win the script language wars, so they developed distutils and released it for the Python 1.6 standard library. Unfortunately, the standard library is where modules go to die, so it didn't scale very well as time went on. In 2003, the PyPI, the Python Package Index, comes online to be a proper alternative to CPAN. And distutils is taught how to create package metadata for this index. This goes on for a few years until setup tools comes. It tries to extend and replace distutils really as the de facto build tool for Python. And it pretty much wipes the floor with distutils. It adds a few options, but it does extend it. And then later in 2008, pip now builds on top of setup tools, and pip is the way to manage your Python packages. The one thing you can notice with this is that everything builds on everything, right? Which is great, because if you had a package with a script written for distutils in 2005, that still works today with setup tools. You only need to change the import. The drawback, of course, is that means we now have, 20 years of legacy? And that shows sometimes. In 2000, with the distutils release, it already knew how to build C extensions that, like you see in NumPy, right? It like C code that behaves like any Python library. But this is largely intended for distribution, and it shows because it provides you very few tools for development. So let's look into using setup tools. What we're going to do now is we're going to take and actually create a package from scratch. So we write our setup file. And this is pretty much the minimal setup file you can have. You import your setup tools, and you invoke setup with a lot of keys that will then be interpreted by setup tools to mean specific things for building and packaging. So we set up the name, the my project name, and we give it a version. We put down Mekazava as the author because he's our proxy and our avatar for this. We slap a BSD license on it because that's pretty convenient, and then we list our packages. In this case, we only have one package, but this will be all the modules you can import after the package is installed. And this is pretty straightforward. It reads easily, and if you have a pure Python project, this is pretty much all you need. But I want to use some C. So I add a little bit. I use the setup tools.extension module in order to declare I want this to be a Python module, but I want it built with a C compiler. So I list the sources, the my package math.c source file, and I also extend the setup call with the extension modules parameter. This is still pretty straightforward, right? So let's actually build this math.c extension. We start by including the Python header, which is the Python API header, and we create a function add. This is just, it sums two numbers, and in fact, it sums two integers. The parse tuple there takes a format string from C almost. It says, I want these parameters to be integers, and if they're not integers, I want you to fail. That's what it says. And then we create a Python integer from that and just return it, okay? Then we register this function in a function table, right? It's just an array of Python's own function definition, so to speak. And then we create a module definition, because we're obviously building a module. You need a module in Python. With its name, math, its docstring. Now I just put down module docstring, but please be a little bit more elaborate here. Something about interpreter state, which usually should be -1. You have all the states in your global variables. And then we give it the function table. And finally, we have this init function that Python knows to look for. That simply creates this module. This is a very simple module with no complex state or object going about, so all we need is the PyModule create function call. This is for Python 3, but it's almost identical for Python 2. So far, so good. Pretty simple and straightforward. And as you can see here, this works. You can try this out, and it will work like this. OK, but I don't want to use C. I want to use C++. So it's actually a little bit unclear. Is the blue color very difficult to see? It's pretty low contrast from here. It's OK? Good. But anyway, so at this line up there, we've added a no except, and we changed the nulls to null pointers just to make sure that this is actually C++. And in fact, it's C++ 11. OK? Other than that, this is the file is identical. And we modify our setup script to use the extra compile args for C++, the standard C++ 11 flag, because we need to tell we want to use C++ 11. This is a little bit problematic, because this assumes that your compiler is GCC or takes GCC flags. Clang does, but MSVC does not. So this will now not build on Windows. The previous one did, because it didn't take any parameters, but this will crash on Windows. This is obviously not great, because one of our requirements was, of course, to build and distribute for Windows. So what do we do? Well, we move out a check. It says, if this platform is not Windows, we assume we have GCC-style options. And really, we're saying, we assume you don't have an Intel compiler anyway, so just ignore that. And then only if it's not MSVC, we add or if it's not on Windows, we add the std C++11 flag. All right, pretty good. Right now, we should work on Windows. which it does until you realize some people use min.gw on Windows. So this test is not sufficient. And at this point, you get pretty frustrated. How hard can it be to say, I want to use C++11 to compile this code, right? So you start, and then the more you dive into this, the more you realize that building for multiple platforms is just not an easy problem. So this is just for compiler flags, but imagine wanting to find libraries in non-standard locations, for instance, because your base distribution is Red Hat 6, which is very old, and you want to use a newer version of a library somewhere that you've installed locally. It's a pretty common use case, right? So you check, how do other people find non-standard libraries? Well, I looked a bit around on the web, and I found this monstrosity. I don't even know where to begin, honestly. It makes a lot of assumptions that are very easily broken. For instance, that the library is in lib and not lib64. So on very many Red Hat-style layouts, this will not work. This will definitely not work on a standard Debian because it puts them behind architecture triplets. So this is very brittle. It probably works on the developer's machine because he's put it out like that, but this just is not portable. And this is something I see time and time and again with these setup scripts, is that they make these kind of assumptions because covering something actually robust is very hard, and there's no mechanism for controlling it as a user. But then you look at the help, right, for building extensions in setup tools. And then you read this. You can pass it the libraries option, which search for external libraries separated by the semicolon, which is pretty common Unix relic, and a series of directories to search for. And you figure, well, with that you can at least say, all right, so if you have your non-standard libraries path somewhere, give it to there. It's okay until you realize you also need its include path, and then you struggle a bit more. So you call that in and say, use that. And that should work fine until you run it on Windows, in which case this crashes. No recovery. And you feel like this. It's very painful being there. And then things get a little bit worse. Because building C++ comes with a lot of issues. You have very different compiler options, depending on your compiler version and, of course, which compiler you're using. There are multiple versions. There are multiple versions on the same machine, right? You might want to use Clang on a system where the default C compiler is GCC, right? You maybe want to use a newer GCC than the one that's in user bin. Like, how do you deal with that? You have platform-specific options. Sometimes you have configuration you only want to do on Windows because Windows has some peculiarity that the other systems you support don't. And you have your binary compatibility, which is an endless nightmare if you start struggling. And then there's more. You have conditionals and options in your build logic. For instance, do you want to support both using and not using BLAS? And then you have a fallback code path, maybe? How do you do that, right? You have system differences. Imagine you want to use one of the most common ones is network to host byte swapping, which is just fixing NDNS. On Windows, that is in the WinSock header, right? But on Linux, it's usually in a sys-inet, but it could also be in ARPANET inet, I think it is. And it has like 3-4 headers it can be in. And that's just Linux. And then you have the Mac, which also has different directories. And if you want the BSDs, and they support it elsewhere. You have build time dependencies and code generation. An obvious example there might be Lex and Bison. But there are, of course, others. And you have runtime dependencies and their transitive links. Right? So if you're linking against a library, and that needs another library, you need to link against that third library too. And you need to get that information from somewhere. And then there's the problem of development. So let's assume that you write this function. It's templated. It's just a division. But I gave it the name div. And you put it in a math HPP header in your project, right? This is a pretty straightforward divide in C++. So you have that. and then you add you register it in the function table, add it to the module, and you run it, and it works, right? You can divide numbers. Great. And then you realize that if you divide by 0, you get a floating point exception from your operating system, and it kills your process. That's usually not an acceptable way of having a library in Python work. You would want a runtime exception in Python that you can then deal with appropriately, right? You don't want your process to be taken down, especially not from a library. So you change it a little bit to actually check, is the right-hand side my divisor 0? And if it is, just raise the divide by 0 exception. And if not, just perform the division, right? Still pretty straightforward. So you do this, and then you build. OK? And you run your test again, and you still get the process termination. So what happens here is that setup tools doesn't acknowledge the fact that code changes in headers can lead to changes in object files. It doesn't track that dependency, which is not very convenient when you're having templated code, which is very common in C++, that you tend to factor out into headers. It only sees that the source files are unchanged and never considers the fact that headers might contribute to the need of a rebuild. And you feel like this. You scream very loud, both internally and maybe you scream some externally too. So then the question is paradise lost? This illustration by Gustave Doré is called The Fall of Lucifer, I think in English. And it depicts Lucifer being thrown out of heaven. The scene from, well, Paradise Lost by Milton. But of course, the talk name hints of a solution. There is, in fact, a new tomorrow. So when I discovered this, it was one of the happier days of my life, I have to admit. There is a package called scikit build, which was started in 2014 at a conference for SciPy. And the scikit, or the SciPy people, they build a lot of code that depends on speed, because a lot of it is numerical and mathematical, and that's generally not very pleasant in Python. And they too kind of felt that the tools they had for building and managing and developing this were inadequate. So they created this package, and as it says on their README, the scikit build package is fundamentally just glue between the setup tools Python module and CMake. So say what you want about CMake, about its syntax and its sometimes funkiness, but it's pretty good at what it does. So for instance, referring to the problems we saw earlier, you can find package to actually detect libraries for your runtime dependency, and then, of course, link against them. And more importantly, CMake assumes that it's sometimes interesting to point to specific versions of that library at configuration time. You can find your compile time dependencies. Like if you depend on Flex in order to create a parser for your language that you want to expose in Python, you might want to run Flex as a part of your build pipeline. Of course, you can link libraries, and CMake's target link libraries actually manages to deal with transitive linking, which is quite useful once you have non-trivial dependencies. You can portably set your C++ 11, 14, 17, or your standard across compilers, and CMake knows how to sort the flags out. You can check for what compiler am I using in order to set compiler-specific options, instead of hoping that operating system also determines compiler. You can check, does this compiler setup have this include file available? And if so, should I then include it or set a specific flag or not? And of course, you have your options for build and runtime. Like, do you want to build shared libs? Do you want to link statically? You can do this. This is what it looks like. This is what scikit build looks like in practice. And I have to say, it is remarkably similar to the pure Python setup tools example. The only difference is that you import skbuild for scikit build instead of setup tools. That's it. This is really it. So Python, the Python build script is actually not really aware that you're relying on C++ code at all. And this is the CMake lists that powers it. So I'll just go through it real quick. You'll specify your minimum version. That's very useful in order to know what features you can at least use. And that will throw the appropriate error from CMake. You say that I want to use C and C++ language and linkage. And in my case now, set the 11 standard. And then you find package this Python extensions thing. Now that's scikit build's own CMake magic thing that you need to just include. That should always be there. And then you add your library as a module like you would do with any CMake project. Make sure to call this Python extension module function, which is provided by the Python extensions CMake module from scikit build. And then, of course, I've just demonstrated here. There you can check for compilers. You can do anything, because this is just a regular CMake invocation. Finally, install your target into your Python directory, your package directory. If you want to link against anything, then you just find package. For that, hopefully it provides a CMake file for you, or at least a CMake config for you, and you just link. If setlib would have had any other things it needed you to link against, or any definitions you needed to set, anything you needed to include in particular, that is now handled by the target link library logic in CMake. It's a much improvement from the find Dakota paths that we saw earlier. Okay. As I mentioned, sometimes you want to use specific versions of a library. And CMake assumes that you want to set those from the command line at configure time. And of course, scikit build allows you to do that by, after the double dash, you can now pass just regular CMake arguments. These are regular CMake arguments to say, look for setlib in that directory. So remember this from before? If we had done this, but with scikit build instead, this would have been the outcome instead, which is what we had hoped to see last time. So we're just going to have a brief intermezzo from the scikit build, because at our everyday work, something like this is what you want to be doing. This should be enough for your development. You want one entry point, you want one command to just do everything for you, okay? You don't want to have to manually remember and run multiple build systems in sequence. That should all be handled and automated for you. So of course, we do that. And how we do it is that in our case, at my job, we use CMake for this. We use CMake as our sort of puppet master to control everything. It didn't have to be. It could have been scones, it could have been Bazel, it could have been build2, it could have been any of the others, but for us it's CMake, and it's worked very well for us. So let's assume we now have a project that laid out like this. We have a core library here that everything depends on. We have our Python library that also depends on the core library, right? With the my package that we saw before. And just for giggles, I added another language to see you have all these, built languages in parallel, language support in parallel. And each of these directories come with their own CMake list file that then manages how to build, from there on down. So let's look at what that looks like for us. So we add what we call a custom target. Custom target in CMake behaves like your add library or your add executable, except that it's always considered out of date. So CMake will always try and rebuild it. We give it we give the target a name. We want it to be included in all, so we don't have to specify that we want it built. We want it always built. And we specify in Python's case that we want to run this in the source directory of Python. Python tools are very, in my opinion, obnoxious in that they tend to already pollute the source directories a lot and do a lot of their work in source directories, because Python is just source code in its distributed form anyway. So we do that in order to choose the path of least resistance, and you don't want to spend much time fighting build systems. So we add a command where we have the path to our Python and the path to the setup file. And we run build extension with in place. And I said, we're now polluting the source directory, but scikit build already masks that behind its own sk build directory, so that multiple builds in the same tree for multiple Pythons will already be in separate directories anyway, so it's not that big of a deal. And setup tools will regardless pollute your directory. And it's kind of accepted in the Python community, so I consider that a decent trade-off. And we run the build, but we make sure that the CMake executable is the same as the one that invoked me, and the generator is the same. So if you ask for Ninja, you will get Ninja also for the Python extension. And then we pass the path to the core that we now depend on as a parameter to CMake, so that it tries to link against the freshly built core library, right? So that if we do make changes in our development tree, that will be picked up by the package. We're using RPath for that here as well, but that, of course, is something you wouldn't do when you install. Then you just rebuild it without the RPath, which is quite nice. OK? And that's really it. Now, it's always built after core, so that dependency ordering is in place. And it just defers all the work and decision of building Python to setup tools. It's granted, that is invoked every time, even though there's nothing to do in the Python extension. But checking that is pretty quick, because that too uses CMake and just a teensy bits of logic. So it's not that much of an impact on performance. OK. The next step is building stuff, and building it in parallel and testing it. So here we have a picture from a shipyard in Belfast. That's the Olympic and the Titanic. And I think it's a pretty fitting analogy for what we're about to do, because one of those had a very long and happy life, and one, well, didn't. Because we want to build everything, and we want to build it everywhere. So this is pretty good. This is what we can now do. By running setup.py build, we can build our project, and we can test it with setup.py test. But in my opinion, this is still a little bit too manual, right? It's way too manual, because now I need to actually go in somewhere and type that command. But remember, we support 3 operating systems, and we support multiple Python versions. And we've learned one lesson over the years, right? And it is that things that you don't do automatically, you just won't do, right? So anyone experienced that, presumably, that you're supposed to test for 10 platforms, but you test on your one, the one you're at, right? To avoid that, we want to automate it. So what we do is we use a CI service. In our case, most of our projects are open source, so we use cloud providers for that. We use Travis, Circle, AppWeaver. I think we use both pipelines, and there's one more. They're all pretty much the same thing. But the gist of it is that they will check out your code whenever you do something, and they will run through a job. And we'll go over that. So we have first the machine definition, I've chosen to call it. So in this case, we're saying we want a machine with Linux. We want to test it in your Python context, and that context, is, of course, is provided by Travis. And I want to test these versions, 2.7, 3.5, 3.6, and 3.7. Obviously, actually, this won't work for this project because it's Python 3 only, but that's how it should be. So this now specifies the machine, and in fact, it specifies 4 machines, 1 for each Python version. And then we have a script that it should do. We want it to install our requirements, and we install another one that we just run out there, which is called Bandit, which runs some static analysis on it. And the nice thing about that is that when we do something, we don't have to remember to run Bandit, because it's always done there. And more importantly, third-party contributors to our open source project don't have to deal with the fact that we also would like to do static analysis on their code, because we do it for them. And that helps the contributor experience tremendously. If a new developer joins your team and wants to contribute something, wants to do some work, a lot of these details that takes a long while to get into habit is also done for you. So we have a massive safety net. And then finally, we do the thing where we, in our case, run CMake, and we test it. So this is now done all the time on Travis. Jobs are triggered by changes to the repository. Okay? So whenever there's a new pull request, whenever there's a new commit, whenever there's a new merge, and whenever there's a new tag in Git, these jobs will trigger. I mentioned we also used AppLayer and Circle, and that's in order to also cover the Mac and Windows, both from multiple versions of the Python runtime, but also multiple versions of the operating system sometimes. This is what it looks like in practice. This is from one of our projects where I have merged. I didn't find an open one when I made this. So, but here you can see 11 jobs have been run to test different configurations with different parameters and different levels of strictness. They're all successful, so I'm pretty confident now there are no new and obvious problems introduced by this. It helps us catch errors very fast, and it helps us move very fast. And honestly, I would never develop without it. I think it's time to reinvent the wheel. This illustration shows up if you Google reinvent the wheel. I don't know what it is. But let's reinvent the wheel. So the wheel is the format for Python packages that I would recommend you use these days. It has a rule set for communicating what exactly it is. It requires a name and a version. You can optionally add a build number. It requires your Python version, your ABI version, and ABI name rather, and then your platform. And this is in order for pip to know, am I able to install this package? So let's go back and we run the project again. We run the build, the be this wheel, on my Debian 10 Buster machine. And it creates this wheel, and you can see it's the name and version, the Python version, the Python ABI, and my platform. And these are the contents, okay? It has the init and the core, as we saw, and this now math cpython linux.so, right? So that would be the extension. And then the metadata that you saw before. This is sort of the anatomy of a wheel. But there's a problem, because we already linked against zlib, and there's no zlib on the user machine, at least not an appropriate zlib. So how do we solve that? Right? Well, we distribute zlib with the wheel. Right? You just bundle it in there. There is a tool called audit wheel, which does exactly that. It looks at what libraries do I need to load this module. All right, I'll grab those and I'll put them inside the wheel. That's exactly what audit wheel does. And then when you look at the contents of this wheelhouse, after running this on my Debian 10 machine, you get this. So the big change here is the .libs directory, which includes lib standard C++, libc, libmath, and libgccs. We'll go into why in a little bit. Oh, and yes, also, of course, libzat, which is the one we wanted to make sure. But this now actually include the transitive dependencies, too. It's quite nice. Just a brief note. We wanted to automate everything, right? But we had a manually set version number before. That does not work, because you will forget to update that number whenever you release a new package. Fortunately, there is an extension to setup tools, which is called setup tools SCM, that if you specify use SCM version as a setup parameter, it will pull the version, the last tag it saw, or the quote-unquote newest tag it saw, and write that as the version file. With that, you never have to think about version again, and we have a single source of truth, which is the git tag. And it's arguably, or maybe even obviously, the most authoritative of any piece of information in terms of versioning for your project. So we're lowering boats because we're very close to the target. And if you did whaling in the 19th and the 19th and 20th century, that's what you would do when you would spot a whale. The classic "there she blows." You will then lower your boats because now it's hunting time. This is an illustration from Moby Dick. Because we're close to the target and we're going for the kill. The problem is, as you notice, the name of the wheel was Linux, right? That Linux is not redistributable because there are many different flavors of Linux and many different versions of both the kernel and the core libraries, and that might not be compatible. Fortunately, the Python Packaging Authority, the PyPI, have this definition called mini Linux. And the idea is if you build your library on a very old system for a very old libc, generally it works everywhere. It's a pretty good observation. They call that the mini Linux. That's a specification released by them. And if the image was mini Linux, it would be redistributable, right? So I could install this wheel on my Buster machine, but I wouldn't be able to give it to someone else and have them install it. So if I run the same thing on a Red Hat 5 machine, right, that we did on Buster, we would actually get a mini Linux wheel out, okay? But I don't have a Red Hat machine with Red Hat 5. And I don't have a Windows machine. And I don't want a Red Hat machine running just to be able to build and distribute my library. So how do we address that? Well, there is a very good reason for me to use the phrase machine definition when I talked about the Travis job. Because the Red Hat 5 is just another machine. And the whaling theme was not by accident. So what the Python packaging authorities do is that they distribute this Docker image with Red Hat 5 compilers and some pre-installed Pythons intended for building these packages for any Linux. And we already have an infrastructure in place to do this automatically, which is our CI pipeline. So that's what we do. To automate that, there is a fantastic package on the web called Multibuild. It's pretty much designed to be used by Git clone that automates a lot of this, setting up or getting the Docker image, getting into it, building it in there, copying back out, all that jazz. Matthew Brett is built and maintain it. He's very helpful. Send him a message if you need anything. But if you put this in your before install, this is all from the documentation. You source the common utils and the Travis steps. It determines if this is a Linux or an OS X Mac OS job, and then run the before install to just set up the environment. With that, it will pretty much build a wheel for you. A complete example can be seen in the docs. And finally, we add a deploy section. So at the end of every successful job, Travis consider if it wants to perform this deploy. It uses this conditional here to determine if it should do it or not. And I'm saying if this build was triggered by the push of a new tag, you should do the deploy step, where it builds the package, it builds the wheel, and it tries to upload it to PyPI using my encrypted credentials and username. So my encrypted password and username. And that turned this into a true one-click deploy, because the only thing I now have to do in order to distribute my package to every platform for many different Python versions is to push a new tag or do that create release on GitHub. This is true one-click deploy because of that. And of course, I know this will work because I've already built and tested it through every single commit since last release. And here's our end game. Now, with all of this, you can run pip install my project for fun and profit. This is Mekazawa distributing stuff for us. He's a little bit old school and uses a CD. So let's look back at what we just saw. So we've created a package. Okay. We built an extension on multiple platforms with C++. we assembled a wheel, we bundled its dependencies for multiple platforms, and we automatically tested and published it. I wrapped this up into an actually runnable example. You can find it at GitHub /Equinor/scikit-build example. It's pretty much complete, although the code and all that is trivial, but it's a pretty good starting point if you want to build a Python library with C++. Finally, I want to give a big shout out to the main sort of tools that go into that. It's scikit-build from the SciPy crew. The maintainers are very helpful if you have questions or patches for them. They're very grateful too, which provides a set of tools. And CMakeGlue, it's a shout out to Matthew, Brett, and others for multi-builds to automate the wheel building in a CI context. And of course, the setup tools SCM for actually making our lives livable dealing with versions, because I may or may not have updated the wrong number very many times. Thank you. I think we might have time for some questions, if there are any. If not, then enjoy the rest of the conference. Okay? Yes.
Regarding the dependencies.
Yes.
So that means that you have a finite set of platforms and configurations that you know, so that you have to build, like when you say min or everything. If you want clive, you have to actually compile and put it and upload every different version.
Yes.
And then it will download just the ones that they need.
Yeah. Because they use the platform tag information. That's, of course, your Python knows what platform it's running on, because it knows, what system you're on, and it uses the naming information in the wheel to determine, is this wheel suitable for me, and then it pulls only that, and then that should then hopefully include what you need.
And if it's not a compatible platform, is the error message helpful enough?
It just won't find the package. No installation candidate, it'll say. Okay. So if there's a package that's only released for Windows, and I try and install that name with my Linux machine, it will just say no installation candidate found. And then, of course, it will also try earlier versions until it finds one that matches. And if none are available, then it just gives up. Then I think it just says no installation candidate. Any more questions? Yes?
Yeah, if you already have the dependencies on your computer, does it check to see if it has to download?
No. If you bundle the objects, it also, what the audit wheel really does, it copies the objects into this .libs directory, and I think it sets up the RPath to say use that one. So it's effectively a hard linking, a static linking. But no, it will not consider local candidates. If you don't do the audit wheel step, it'll of course just use the regular loader semantics. But at that point, you probably want to build from source anyway. Yeah? Any more? All right, then I wish you a good day and enjoy the rest of the conference. Thank you very much.